Hey, welcome back. I'm just checking our stream, making sure that we've got sound and video. It seems like we're up and running. Hopefully internet holds out today here in Engineering Building 2. And today we're looking at project number 3, this engineering design for rocket flights. And if you think about like how this project connects to what we've been doing in module 3, this is very similar to a shooting method where we know the beginning state and we know the end state. So we know here and we know there, and we're trying to pick an initial condition. Here it's not really an initial condition. We're choosing like how much mass we want to burn per second, like how many kilograms per second. But it's the same idea, right? Like we need to define a differential equation, make sure that we can integrate it correctly. And that's what the first couple of steps are in the project, is like verify that our integration works correctly. And then we can create like a function, same thing here, where we made like a function of v, but next we're going to create like a function of dm dt. Just as a quick like high level, why are we doing this project? And if it seems difficult, it's probably it is difficult, right? Like this is rocket science. This is what people in NASA spend their careers kind of working on. We're getting like a tiny glimpse of rocket science, like kind of building these differential equations, but it's still kind of fun to play around with like how we can engineer things in this way. And we have like two different approximations. Two different approximations. One is that we have MA of our rocket. The thrust depends on the current mass of the rocket and how fast, and then this propellant speed. And then we're fighting against the forces of gravity and drag. So that's kind of, and we're only moving in one direction. So it's one dimensional. We're just going straight up. Versus this next equation, which is kind of the simple rocket equation, where we have mass times acceleration, and the only force acting on our rocket is the thrust. Another way to think about this is that these equation 1 and equation 2a are the same if dm dt is really large. So if dm dt is much bigger than, or at least u times dm dt. But if it's much bigger than mg, the weight of the rocket, and it's much bigger than this force of drag, then this is an exact equation. And the reason that we want to consider this one is it has an exact solution where the mass of the rocket divided by its initial mass is related to its current speed. All right, so let's jump right into kind of working through this. So this simple rocket, I didn't see anyone like have too much trouble here. I'm just gonna take all this. And the only thing I need is this u over m. And then this one is going to be my d state of 2. This is a common tripping point, is that although we're using a positive dm dt here, it's got to be a negative d state 2, because state 2 is mass. And sometimes it helps me to write that out as like y comma v comma m equals state, so that I can grab those 3 values from the input and plug them in as v, m, and then this dm dt is the thing that I'm entering up here. So this is one of my default variables for now. And so one thing that I noticed is that people were trying to show convergence to like this final, like thinking of this as like a single value of like final mass over initial mass. So let's take a look at that. So we have like final mass, initial mass. I know U is this 250, and so MF over M0, and I'm just writing this out. Let me just grab this equation. So if this is my, I can say np.log of that, and now I've got a negative U times that. So I saw some people kind of think of this as like, all right, the final speed has to be 402.4 meters per second based on this equation. And that's kind of an interesting way to think about this. So what we could do is more of like, rather than trying to show as we integrate this V and M that they have this relation, that there's like a log relation between the current velocity and the current mass, we could say like, all right, my final velocity should be this, and if it's not that, then there's an error in my integration. And yeah, so let's try. So I saw some people from scipy.integrate import solve IVP. I saw some people using this solve IVP method, and it's a nice way of doing things. I guess the only thing with this is that we're not going to be able to control our time steps. So let's remove that. We're gonna do it so here I've got, let's put this as N equals, let's just start with 11 steps. And my state is going to be an array of zeros. It has t, the same number of values as t in it, but it has 3 different states. Oh, not 30. And then my state of 0 is 0, 0. So 0 position, 0 height, 0 velocity, and 0 point, and then n0 as its initial mass for I in range 1 through length of t. State of I equals some kind of step of state I minus 1. And my right hand side is going to be that simple rocket with a time step of dt. So I should define dt, right? And so what I'm doing, I'm building all this based on the same kind of setup that we had in the readings that we were looking at. So let's come back here, and I can use this Rungakutta, like RK2 step. See, it has a second order convergence. That'll be a good one. So we'll define that in here. Paste that in. This is an explicit method. So if I use this again for the next part, I'm using an explicit method because there's no convergence check before I move on to the next state. I'm just taking values of, even if I took 30 different values, like state, right hand side state dt 1/2, like I could do like 1/30th plus 1 plus 2/30th plus 3/30th. But if it's all adding a whole bunch of things up and averaging the result or doing some other complicated step, if it doesn't do any kind of convergence, then it's not implicit. It's still an explicit method. Okay, so we have that RK2 step. That's what I'm trying to do. And let's plot the mass versus the speed. And what I see here is that it looks like some kind of logarithm function, or a negative logarithm kind of function. But again, what I'm trying to do is figure out, like, is this, oh yeah, let's print this. Is this 402.4 or is it 401? So instead of just like plotting this result, what I could do is say final speed. So we'll do a Tsiolkovsky final speed meter per second. So this is my Tsiolkovsky final speed, and then RK2 final speed is and here I just want the last value in that second row, or sorry, second column. So right now my error is 2 meters per second, and that's not bad. Like 2 over 400 is pretty small. It's not a very big error, but I can get that better. Like if I say that this is 101, now I have 402.35 and 402.34, even smaller error. And if I'm doing it in this kind of method of like just checking that, what is the final state? Like how close am I to this equation in that last value? Then we can do the same kind of plot as we did. The same kind of convergence plot, right? We can say, all right, here's my delta t, and how close am I in terms of error, because I have an exact function that I'm comparing to. So what I'm going to do is take all this, bump it over, and this one I'm going to say for n in 11, 101, 1001, and maybe we'll do a couple in the middle, 501. I like to add an extra one in there, and 51. And I'll have like a DT vals and then a air vals. I'll keep append. Usually I don't like to append values because sometimes I end up with like off by 1 plotting errors, but we'll deal with it for now. I'm just turning some stuff into variables so I can reuse it. And down here on these error values, I'm going to append this speed minus the actual speed. And really, I want the absolute value, right? I don't really care if it's a plus or minus difference. I just want to know. Okay, so let's try that. DT vals, if I could spell. And sure enough, by time I'm at 1,001 steps in this short time frame, I'm basically at the same number, 402.3593, We're really close. But now I can take this and take a look at DT vals and air vals. On a linear scale, it looks kind of weird, so let's put it on a log. And now I can see same kind of, and what I should see is actually second order convergence, right? And I might end up, yeah, it doesn't like, so I'll turn it into an array. I see second order convergence with this Runge-Kutta-2 method. Put squares there, and we'll put this dash line like that. So this is a nice way of approaching this problem of thinking about, like, okay, Tsiolkovsky says the final speed should be this. So if I don't get that same final speed, then there's an error. And in engineering, the question is always how much error is good enough. We never have an exact equation. Like here, we happen to have an exact solution that we can get closer to, but even this is, it's an idealized solution where the force of thrust is so much bigger than everything else acting on the rocket. So this is, yeah, the same kind of approach that we had done in the homework, like demonstrating convergence. And there we can even show like how quickly it's converged and the order of the error. Make it 10,001. Yeah, 10 to the negative 6, and like all these are really small values, and these are absolute values, right? Like it's not relative errors. So we could also say divide by V. And if I take the relative error of like the error values divided by the actual speed, now we're looking at 10 to the negative 8, 10 to the negative, even at the biggest time steps, 10 to the negative 3%. So 0.1, yeah, 0.1% error. And so the other way, if you were thinking about things this way, this is a great process to think about. But some people were just trying to figure out, like, how do I take this equation and compare it to so how do I take this, oh, not that one. How do I take that and compare it to plot, and I want to do state of colon 2, so that my mass versus my speed. So I'll put that as like little circles. There's going to be a lot of them because it's, so I've got all these circles. And does that match this line? That's the question that I'm trying to ask here, which I can figure that out because I can say, I can take this equation plug in all the masses that I know. So this is, and I don't have to use the actual calculated masses, but I can if I want. And take this equation, and instead of using MF as just one single value, I can plug in. So now what I'm doing is saying that the mass is the speed, but it's the speed in this function of mass. So whether I create my own value of mass or I use the ones that I actually calculated, and let's put that as like a black line like that. Now I can see that it's definitely converged. And even if let's put another one at the very end of like 7. And what I can see here is that if I have only 7 steps, they're pretty close, but there's definitely some error. Like these the dots line up, the markers line up with the line for small changes in mass. But as I keep moving along, I'm increasing the error, which is what we saw here, is that the smaller our time steps, the less error we have in that final value. Yeah, so both these methods, whether you want to show like if someone's looking for like, how does this method converge? This is a great way of saying like, all right, this is what I call error of like final speed. And let me look at a log plot of, as I keep decreasing time step, what happens to the error along here. It gets harder to do that when you use built-in methods like solve IVP, because you don't have control over the time step. Let's see. Events, args. So you can choose what times you want to evaluate, but it's not necessary. But sometimes it'll do multiple steps on the way there. Options, first step. Yeah, and like here we can choose the first step, but it's going to use, it has its own algorithm to figure out what the following time steps will be. Jacobian. Yeah. And we can choose a minimum step size, but we can't choose a maximum step size. So that's what I'm doing here. Like if I want to check like a specific method or something, like how is that method converging, then I need direct access to what that time step is. But if I just want to show that, hey, my integration, no matter what integration I used, it lines up, a graph like this is great to say there's no difference like when I'm looking at this. All right, cool. So then we can move on to Rocket, where now we want to try 2 different integration methods and compare it. And let me just grab this stuff. Paste that in. And, oh, I don't need that again. There. Now the extra part is that subtract acceleration due to gravity and then subtract a c over m times v squared. So an extra, and this drag constant, this one kind of builds in the area of the rocket, its coefficient of drag and all that. It's just one value saying that c times v squared is drag. Cool. And now let's try that solve IVP method. Just change it up from scipy.integrate import solve IVP. And I'm going to give it my rocket equation, give it the initial and the final time, and let's double check. Do I have a final time defined? I don't know why I'm doing that. I don't. So I'm going to copy some stuff and then delete some stuff. So I have rocket. I just want to set this thing up. I don't, well, yeah, don't need this for now. I don't need those. Don't need that. So here I'm going to say t -1. So I'm going to go from time 0 to this time. And I could define that as like a TF, right? Let's do that. And yeah, let's define n. 51 steps. Why not? Now I have to give it my initial state, 0, 0, and then M0. And if I want, oh, why is this? Whenever it misaligns things, it drives me a little crazy, just a little. I'm gonna say T eval is T, just so that I can specify how many data points I want. Otherwise, it kind of breaks it up a little bit. So let's try this just to start, because I already knew that I was going to get an error. It's telling me that something on this line is wrong. The way to go in there is come down to the bottom. So it's telling me that it can't unpack a non-iterable float object, so type error. So for some reason, it's trying to take the state and turn it into YVM, but it's not working. It's like, well, why not? Why isn't this working? So let's look at solve IVP. Actually, if we want, we could try, because this is the modern programming is not that you look up the documentation. That's how I learned how to program. Modern program is that you say, ChatGPT, this is my error. I got this error running solve IVP. How do I fix it? Okay, so it could be that the initial condition is wrong, but I did it correctly, at least from what I remember, unless there's a typo. And I guess it's already and there's a nice debugging step, like printing is a nice way. I think that's why it's always the first thing you learn is how to print something, is that's the best debugging step, is printing out what is your variable. But let's take a look at what it's suggesting for rocket as the answer. The first inputs are t and state. So let's come back here. When I look at my input, it's state. The first thing is state. So let's just add a t there, even though I don't have time as part of this. But that's okay. And now no error. All the errors went away and things worked. And the reason this works is that solve IVP, here, this is my life hack. Skip down to the examples and take a look at even a minimal example. It's always expecting t and y, because in general, differential equations have some function of time. So when we're using solve IVP, it's always expecting time to be part of it. In this class, we've dealt with everything that's like time independent, like all the homogeneous solutions. Okay, cool. So now I can say plt.plot sol.t and sol.y of 1. Oh, no, I'm like, what am I doing wrong? So I went mass and speed. So I can think about like, all right, well, is this close enough to that first equation that I created? So I'll come up here and grab these two, right? And same thing here. I see that for small changes in mass, it agrees pretty well, but over time it's getting worse. And it should be different, because here I'm including gravity and drag, and in these two equations, gravity and drag are assumed to be 0. If you want to change that, we could do this. Lambda t comma y of rocket t comma y dm dt equals dm. So this is one way of changing the arguments. Let's create this little anonymous function in here. And instead of 0.05, let's make it 20 times larger. We'll make it a kilogram per second. Now I see much better alignment with that Tsiolkovsky curve, because now thrust is a much bigger force than gravity and drag, even for that. And this is all happening really quickly. So total time was 1/5 of a second, and it reaches 400 meters per second. So basically an explosion, but it does match with my Tsiolkovsky equation now. And what I've done here is use the default solve IVP, but I want to also use an implicit method. So looking at this is the documentation for solve IVP, which I can also get with solve IVP question. It'll show me the same thing. There's this input called method for solve IVP. So the default is telling me that it's RK45 explicit, but I can also use like a Redao implicit Runge-Kutta or a BDF implicit multi-step function. LSODA, this one doesn't really say if it's implicit, explicit. But anyway, we're kind of doing exactly what it says, is that use a default explicit method to start, and then and then move on to like Redao or BDF if you have like the stiffness has to do with like how big of a change in derivatives are there. So if like one thing is changing very slowly but something else is changing very quickly, that could lead to a stiff problem. All right, so we're gonna take this, I'm gonna call it my RK45 solution, and paste this down here and call this my my rad solution, because I'm going to say method equals Redao. This one shouldn't change at all. We'll put this one as like red squares. This one's gonna be blue circles. Solrad. And what I can see is that even, and here, let's change this back to like 0.05, how we started. Even when it's not agreeing with my original Tsiolkovsky like logarithmic function, they agree exactly with each other. There's no real difference between the two. And if I really want to see, if I want to get that into like more detail, I could take one minus the other and see what is the error between the two. And to start, at the start, there's no difference. And again, we're kind of reading this backwards, right? Because this is the initial mass and then we're moving that way. There's no real difference, and then it starts oscillating that way. Or what I could do is, let's take this one. All right, I want to copy it, and let's look at trying to say plus that. There we go. Oh, yeah. I gotta go back up and change this last one to 51, right? So it all matches. And now I can see like what the error is. And again, we were expecting error to build up here. So let's change this back to, we'll go real big. Make it take 0.02 of a second. And now I can see that these red squares are, because it's an explicit method, it's like slowly building up error as the time goes on, versus this implicit method, which decreases, well, I mean, it kind of increases. You get a little bit of better final error, like the final error here is better with the implicit method versus explicit. But we're talking 1 meter per second versus 400 meters per second. So we're getting pretty close either way. Okay, so now what we've done here is we built a simple solution and verified that integrating it works, whether we use handwritten methods or we use computer, like numerical methods. And now we've added some forces to make it a little more realistic. We don't have any way to verify that these solutions are correct, but we can say that that the solution is independent of how we get to that answer. So since we've done all that work, now we can start optimizing. So we have this model that we can use for engineering work. And what I want to do is just grab, and since Redao was a little better, here, I'm going to grab all this and just paste it down inside my solution and then start deleting stuff. Okay, so Redao had a little bit better of a final velocity, so I'm going to use that one as my method. I don't need to say that I need to evaluate it at certain times. And I don't need to define number of steps or print this total time. And let's see, I have an M0, a C, a U. I could leave this and say that this is dm/dt. I don't want to define M0 because M0 is an input, so I don't want to redefine. I don't want to overwrite my input. MF is not one of my inputs. I could add it as one if I wanted, and U is also an input, so I don't want that to be overwritten. This T final depends on M0 MF. All right, cool. Am I missing? Oh, I see. Bracket, parenthesis. All right, cool. So this solution is going to give me the height, the velocity, and the mass all as a function of time. And what I'm trying to do is say that my final height is solrad dot y bracket 0 and -1, so the last value, and my error is 300 minus that final height. And I could say final height minus 300, either way. And this should work, but I don't know until I try it, right? 0.05, -125 meters. Is that right? Maybe, I don't know. Let's go back and check, right? So I have this solrad solution up here. I can say plot sol.t and sol.y bracket 0. And here I go from 0 to 30 meters. Oh, because my I have such a large, so if I have a dm/dt of 10 kilograms per second, I should have an error of around 270. So let's try that one. Yeah, 297. And coming back up here, yeah, 300 minus 20 something, 29 or something. So pretty darn close, I'm pretty sure. Let's make sure. I think we're doing. So then I can use this modified secant method. Since as I give it a value, it gives me an error. Modified secant is going to plug in values. Mod secant of FDM, give it some initial value like 0.05 or something. And then the second input, so that's, oh, sorry, first input is dx. So I don't want that to be, I don't want my initial guess. I want this to say like x0 is that. I want dx equals just something, if I'm guessing like 0.05, I want it to be small, just because it's the step that I'm going to use to create a derivative. So I want really small derivatives. And sure enough, I get a value that 0.08, and the current, so it's giving me like what is the current function. So FDM of this value is -1 times 10 to the -8. The absolute error is 5.95, and then the number of iterations was 4. So in 4 steps, it got to a solution. So since I have that, now let's come back up here and grab, let's just grab all this again. Well, you know what, we'll grab all that. I'm gonna come back down here, paste it, and I don't want, I think I can say that, right? I'm just trying to grab that first. So I can say like, these are the outputs, and then this is my X OPT, or call it like DM OPT, like that. Just so it's a little easier to read. So DM is going to be equal to DM OPT. All I care about is this solrad for now, since that's what I was using. Solrad dot t solrad dot y bracket 0. So I go 0 after 2.5 seconds. I'm at 300, and just, or actually, let's do this. Bracket -1, comma -1. Make a big star marker and say marker size equals 25. Boom! Now I've got this big explosion up at 300 meters, and I am ready to rock on this rocket science problem. But yeah, from start to finish, that's hopefully that helps in kind of guiding. And yeah, there were a few different ways of approaching this, especially at the beginning. A few different ways of approaching that problem. So I wanted to kind of guide where I saw the class, where I saw you guys working, where I saw the class working. So some people were trying to work on this part. Other people were working on something of like comparing that final value, and then building that FDM. This is a great problem solving method, and the general process of this is called like inverse problem solving, where I know how to calculate the height if I have DMDT, but what I'm trying to do is figure out the height. I'm trying to figure out what DMDT that I need to get to a certain height. And that general process is called inverse problem solving, where one direction it's very easy, not easy, but you've already solved the problem in one direction, but you don't know how to invert the problem. It's not like a lot of algebra equations, we can just invert the equation. But in this case, we have a complex numerical method where we can go one way and get an answer, but it's hard to get back the other way. And we've come across that a few times now in this computational mechanics class. But it's a great way of thinking about problem solving. So I hope this helps in your engineering career, and then in particular on this project. And I will see you next time. Thanks a lot.